Welcome to the class again. We were discussing about tributyltin hydride. Now we will discuss about Barton Mc Combie deoxygenation. Barton Mc Combie reaction or Barton Mc Combie deoxygenation. What is this Barton Mc Combie deoxygenation? Reductive removal of hydroxy group using TBTH is called Barton Mc Combie reduction. How do we reduce this hydroxy group? In order to reduce this hydroxy group, we need to convert this into halogen first. Then we can easily reduce halogen with TBTH. So the entire process is called Barton Mc Combie deoxygenation. In this case, first the hydroxy is converted to a good leaving group. In the first case, hydroxy is protected with the tosyl group. So O-tosyl is a good leaving group. Then it is converted to halogen by treatment with sodium iodide. Iodide is not a good nucleophile. So generally what we will do, we will apply thermal conditions. That means we will heat it. Under thermal conditions, iodide acts as a good leaving group, OTS will be leaving. When it is halogenated, of course we know we can treat that with a TBTH under radical conditions. So we can reduce that hydroxy group. This is reductive removal of alcohols. Reductive removal of alcohols. So this is what Barton Mc Combie reaction. Conversion of hydroxy group into halogen either directly or by two-step process. First conversion of hydroxy to a good leaving group, then substitution of this good leaving group with iodine, then reduction of alkyl iodide with TBTH under radical conditions. So this is what is called Barton Mc Combie deoxygenation or Barton Mc Combie reduction. Now the same process can be applied effectively when we convert this alcohol into a xanthate ester, a thioester or a xanthate. Thiocarbonyl, DMAP, and then dimethyl aminopyridine, which is a base. Base will pick up the proton here, then O minus will attack here, Cl minus is a good leaving group. So what we are doing here, we are converting this into thioester. We are converting this into a thioester. This thioester can be reduced using TBTH. So what is the product here? This is the product. I'm sorry. So instead of converting hydroxy into a good leaving group, then reduction with TBTH, we can convert hydroxy into a thioester very easily. It is a single step process. So convert hydroxy into thioester, then thioester can be directly reduced to the thioester can be reduced. So the overall process is reduction of this alcohol. Not only thioester, we can also convert alcohols into xanthates, CS2 methyl iodide. Sodium hydride will pick up the proton from OH. O minus will add to CS2. C double bond S, single bond S. S minus will be alkylated Me, iodide will be leaving. This is called xanthate. This is called xanthate. Okay. Xanthates can be reduced very easily. I'll give the mechanism. Xanthates can be reduced with TBTH under radical conditions. This radical will attack on sulfur, then double bond C double bond S will be polarized. One electron will be polarized towards sulfur so that a tin sulfur bond formation occurs. Another electron will be polarized towards oxygen so that carbon oxygen double bond will be generated. Then this oxygen carbon oxygen bond will break down in such a way one electron will be polarized towards this bond formation, another electron will be polarized towards carbon. So when we treat this with tributyltin hydride AABN, what is happening? Tin is attaching to sulfur, then carbon oxygen double bond is generating. During that process, the carbon oxygen bond, that means the alcohol which is undergoing reduction, which is removed from the carbon. Of course, then we will the further process will continue, right? This radical will pick up a hydrogen from TBTH. So instead of converting hydroxy into a good leaving group, then substitution with iodide, then reduction with TBTH, we can alternatively we can reduce this alcohol by converting it into a thioester or a xanthate. This is better compared to the first reaction. So alcohols can be reduced under Barton Mc Combie reaction by converting alcohol into either a thioester or a xanthate followed by reduction with TBTH. But in this case, see, when we use a base, a strong base, and we have a chiral center here, this chiral center is alpha to carbonyl. That means when we use a base, the proton on this carbon can be removed. So there is a possibility for the isomerization, right? There is a possibility for the isomerization. So cis trans, we will end up with cis trans isomer, cis trans compounds, right? The chirality will be lost here. Enolization occurs, leading to loss of stereochemistry. So when we use a strong base, the alpha hydrogen can be picked up, so we are generating an anion here. In that case, we may have cis as well as trans. So what we are having, we are losing the stereochemistry around this, right? Instead of getting a single product, we are ending up with a mixture of products. So to just avoid this, what we can do, we can use thioester, where this diimidazole compound, we have already discussed about this imidazole compound, these two imidazole rings are very good leaving groups, right? These two are very good leaving groups. So that means we don't need to use a strong base to convert this alcohol into thioester. Whereas if you want to convert this into a xanthate or a thioester, we need strong base. But because these two are good leaving groups, we don't need a strong base. So a simple base can convert this alcohol into thioester. A simple a simple base can convert this into thioester uh, due to sterical space restrictions. I am writing like this. So without a strong base, with a mild base, we can pick up this proton, we can convert this alcohol into thioester. Of course, then we can do this reduction, right? Tributyltin. I'm using deuterium here, and you write the product and you know what to write, right? So take out this. Generally we used to add hydrogen here when we have tributyltin hydride, but we are using deuterium. So what we will do, we will add deuterium here. See this example. This alcohol is converted to thioester using imidazole. Then there are two possibilities with this. When we treat this, of course, plus AIBN. Now, as I said, TBTH or the silyl hydride can be used. Now, what we will do, we will add this silyl hydride drop by drop to this reaction mixture. What we are doing, we are adding this silyl hydride drop by drop to this reaction mixture. Then what is the product? In the other case, what we will do, we will add this drop by drop to this silyl hydride. Then what is the product? Did you get me what I am telling? First we are taking this in the RB, then we are adding this silyl hydride drop by drop. Then what will happen? When we add the first drop, say for example, when we are adding first molecule, AABN will pick up the hydrogen from the first molecule, then silyl radical will attach to sulfur. So oxygen will be taken away by carbon, then we are generating this radical, right? We are generating radical here, because imagine there is only single molecule of silyl hydride. So when single molecule of silyl hydride is there, we are generating this radical, and we have intramolecular double bond so that it can easily undergo cyclization. 1, 2, 3, 4, 5. So we are getting a 5, 5 fused ring system. Of course, it will be cis ring fusion. Okay. When we are adding this reagent drop by drop, the concentration of silyl hydride is very, very small, right? The concentration of this compound will be large. So what will happen? Instead of picking a hydrogen from the silyl hydride, the generated radical will undergo cyclization. Now what we are doing, we are taking silyl hydride in the beaker, we are adding this this compound drop by drop. That means in this case silyl hydride quantity is very large, the compound quantity is very, very small. In that case, what will happen? Yeah, radical will be generated here. So when this compound concentration is very small and silyl hydride concentration is very large, that means we will have more number of silyl hydrides. Then it is easy for this radical to pick up a hydrogen from silyl, because there are more number of silyl hydrides. So if you add silyl hydride drop by drop, the generated radical will undergo intramolecular cyclization. In the reverse case, if we add this compound drop by drop to the silyl hydride, because more number of silyl hydrides are there, then this radical will easily pick up the hydrogen. I'll give you one more example. So first we are converting this into xanthate. Then when we treat this with tributyltin hydride and AABN, what will happen? It is Barton Mc Combie reaction. It will undergo reductive dehydration. But instead of treating with TBTH, if we heat this, if we apply thermal conditions, then what will happen? It will undergo dehydration, leading to alkene generation. It will lead to dehydration, leading to alkene generation. Okay, here it is just simple, it is simple dehydration process. But what we are doing, we are converting this into a xanthate, and then we are applying thermal condition. Generally, when we want to do dehydration, what we will do, we will treat it with a strong acid so that it will undergo dehydration. But an alternative process is, if you cannot apply strong acidic conditions, then what we can do, we can convert this alcohol into xanthate, then apply thermal conditions so that we will have dehydration. Okay, if you cannot apply strong acidic conditions, this is another alternative. When we heat this, it will undergo syn elimination. It will undergo syn elimination. That means sulfur with its lone pair will pick up this hydrogen, then carbon hydrogen bond will be polarized to generate carbon carbon double bond. then carbon oxygen bond will break down and it will be polarized to this xanthate carbon, so that it generates C double bond S. Then this double bond C double bond S will break down to give C single bond. So the product is C double bond O SH. Other side we have SME. Okay. Of course, it is not stable. Again, it will undergo decomposition, so that we will get SCO and this mercaptor. This reaction is called as Chugao reaction. So after converting alcohol into xanthate, with TBTH, we will remove this alcohol. But when we apply thermal conditions with syn elimination, this will undergo syn elimination. With syn elimination, it generates alkene. So it is called Chugao reaction.